Okay, so we're going to talk about section 3.3 very briefly. This is how f and f prime and f double prime affect the graph of f. Okay, so we've discussed a few examples already in class about this, but I just want to go through a couple of specific examples. So let's start off with we know some facts. We know that one, when f prime equals 0, there is a horizontal tangent line. So horizontal tangent. We know that when f prime is positive, then f is increasing. And we know that when f prime is negative, then f is decreasing. Okay. We know a couple of other facts as well that we'll discuss later, but when f double prime is positive, we know that f is concave up. We'll talk about this in just a little bit. Concave up. And when f double prime is negative, then f is concave down. Okay, so we're going to use these facts to go through a couple of examples. Okay, so example number 1, find the intervals when this function f of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 5 is increasing and decreasing. Okay, so find the intervals when this function here, this polynomial, is increasing and decreasing. So this is a degree 4 polynomial. So the solution to this is we start by taking the derivative. Easy enough. We get 12x cubed minus 12x squared minus 24x. Okay. So I guess the very first thing we should do is set this equal to 0. So if we set f double prime or f prime equal to 0, then we get 0 is 12x cubed minus 12x squared minus 24x, and if we factor this, then every piece of this has a common 12x, so we take 12x out, and we're left with x squared minus x minus 2. I think I did that right. And if we factor this just a little bit more, we get, I think, let's see, we'll have x, one copy of minus 2 and one copy of plus 1. So this right here is the factored version of setting the derivative equal to 0. All right, so this tells us here when the derivative is equal to 0. The derivative is equal to 0 when x is equal to 0 or minus 1 or plus 2. Okay, so let's write that down. So f prime equals 0 at x equals 0, x equals minus 1, and x equals 2. Okay, and I'm just going to rewrite this derivative one more time in factored form. So we get 12x times x plus 1 times x minus 2, because this is going to help us in determining the intervals where f is increasing and decreasing. So I'm going to mark minus 1 and 0 and plus 2 on a number line here. So this is x. And we're going to just determine what f is doing in each of these intervals. So here we know f prime equals 0, and here we know f prime is 0, and here we know f prime is 0. So what's it doing before -1 on the number line here? So if we pick a number that's less than -1, that will make this piece negative, and that will make this piece negative as well, and it'll make this piece negative. So we have a negative times a negative times another negative. So it should be, so that will be a net negative. So in this range here, f prime is less than 0. Okay, so that means that f is decreasing on this interval here. Okay, now what about a number in between -1 and 0? Well, that again will make this piece of the product equal to, or negative, I'm sorry. That will make this piece of the product positive because it's a number between -1 and 0, so that will be positive when you add it to 1. And then this here will be negative, so we'll have a negative times a positive times a negative, so that will be positive. That means that f is increasing on this interval right here. Very good. Now, what about between 0 and 2? The same thing. That will make this positive. This will be positive as well, because we're just adding 1 to it. And if it's strictly between 0 and 2, then this, when we take 2 away from it, will be negative. So we'll have a positive times a negative. So here, f prime will be negative, and f will be decreasing. Okay. And then one more time, when we're larger than 2, this piece will be positive, this will be positive, and this will be positive. So the net product of those will be positive, and so f will be increasing. So we would say that f is increasing on the following interval. So we go back and look. Okay, so when we're in between -1 and 0, I'm sorry, and when we are bigger than 2. So these are the intervals where it's increasing, and f is decreasing on the other intervals. So when we are between -infinity and -1, and when we are between 0 and 2. Okay. So we could use this information to draw something that looks like the graph of f if we choose to. Well, actually, yeah, let's go ahead and do this. So again, recall our function. So can we sketch? So our function was 3x to the 4 minus 4x cubed minus 12x squared plus 5. Okay, so let's try to sketch here. All right, here's -1, here's 0, here's 2. Okay, so let's plot, for starters, where f is at each of these values. Okay, so when x is equal to 0, this is 0, 0, 0, 0. So we have 5. So we're at 5. So our graph will pass through that point right there, and we know that it will have a horizontal tangent line. So let's just indicate that as so. Okay. What about -1? Okay, so that will be 3. Plus 4 is 7, minus 12 is -5, and plus 5 would be 0. So let me just verify that I did that correctly. 3. Okay, so 3 minus 1 cubed would be -1, so that would be 4, so it would be 7. Minus 12, so that would give us -5, so 0. So the graph of f will pass through here, and it will have a horizontal tangent line right there. Okay, what about 2? So here I have to actually do a little bit of thinking. So this is 3 times 2 to the 4, which is 16, so that's 48. And let's see if well, it's going to be something negative, okay? So we'll be down here somewhere. All right, now if we look at what our function has to be doing, okay, I'm going to just slide this paper in here again. So f was increasing from -1 to 0 and 2 to infinity. Okay, so -1 to 0, f has to be increasing. So, all right, so we have to connect to there, and here it has to be well, I guess maybe we should modify this because it has to be it has to have a horizontal tangent line here, and then another horizontal tangent line down here, so it has to be increasing there. And it's decreasing on the other intervals. So here's decreasing, and then we are increasing on this interval, and then we're decreasing the rest of the way down to here, and then increasing thereafter. Okay, so this is a rough graph. Just based on the increasing and decreasing intervals. Okay, but notice how easy that was to draw. We knew it had to have a horizontal tangent line here, a horizontal tangent line here, and a horizontal tangent line here, and we knew it had to be decreasing, then increasing, then decreasing, and then increasing. Okay, so we did this without any use of our calculator whatsoever. So that's one example. All right. So I'd like to outline a theorem that we have. This is called the first derivative test. Okay. It says that if C is a critical number for f, so remember what that means. A critical number is a number where f prime is 0 or f prime does not exist at C. Let's see. So 1, if f prime changes sign from positive to negative at C, then f has a local max at C. Okay, so the picture here is this would be our graph. Here where f prime is positive, here f prime is negative, and here f prime is 0. So we're saying that if f prime changes sign from being positive to being negative at C, then f has a local max. Okay, so this is our conclusion. 2, if f prime changes negative to positive at C, then f has a local min at C. And that's just the reverse picture here. Okay, I'm not going to draw it. 3, then if f prime stays positive or stays negative at C, then f has no local max or min at C. Okay, so here's an example of this. 2 examples. So f could look something like this, or f could look something like this. Okay, so here we see that f prime is positive. Here, f prime is also positive. And right here, f prime of C was 0. So the graph could level out for just a moment and then just keep increasing. And here it's the same thing, but in the reverse. So the derivative is negative here, and the derivative is negative here. Okay, so we could have this sort of behavior. If f prime stays the same sign when we pass through C, then f has no local max or no local min at C. That's the first derivative test. Okay, so let's talk a little bit about concavity. So we've already seen pictures in class about concavity, but let's just recall. So concave up. A graph is concave up if it lies above its tangent lines everywhere. So this is concave up. So I'm going to draw some tangent lines. There's a tangent line. There's a tangent line. There's a tangent line. Okay. F lies, so the graph of F lies above its tangents. Okay. Concave up. And we use this notation in class to indicate concave up. Concave down is the same thing in reverse. Graph of F lies below its tangents. Okay. There's a tangent, there's a tangent, there's a tangent. F lies below all of its tangents, so we write F with that symbol. Okay. Notice these symbols are meant to indicate the shape, the general shape of the graph. And we know what this means. We saw this in class. The second derivative is positive in the concave up case, and the second derivative is negative in the concave down case. Okay. So this is concavity. Okay. So I want to just explore concavity with an example. Okay, but maybe right before we talk about that. So a point definition. A point at which F double prime switches sign is called an inflection point. Okay, let's draw a picture of an inflection point. So if we have a graph like this, okay, right here, right about here, it looks like it's concave up on this side, and then concave down on this side. This point right here, where the graph switches concavity, the second derivative is going to be equal to 0 at this point. Here, the second derivative will be positive. Here, the second derivative will be negative. This is called an inflection point. Okay. So we can determine, just like in the last example, when a function's graph is concave up and concave down by looking at the signs of the second derivative. Okay, let's take a look at this with a specific example. So example, f of x equals x to the 4th minus 4x cubed. Okay, and so the question here is discuss concavity, intervals of increasing and decreasing, local maxima and minima, and inflection points. Okay, and then sketch the curve. Okay, so this is our task. We'll go through this and draw a complete graph of this without using our calculators in any. Excuse me, I'm drinking coffee. In any way, without using our calculator in any way. So here's the solution of this. We're just going to start taking derivatives. Okay, so for starters, the first derivative is 4x cubed minus 12x squared, and the second derivative is 12x squared minus 24x. So these are the two pieces of information we need. So let's first determine where increasing and decreasing. So where f is increasing and decreasing. So to do this, remember we set the derivative equal to 0. So if we do that, we get 0 equals 4x cubed minus 12x squared. So there's a common 4x squared here. So we've got 4x squared. And when we factor that out, we have x minus 3, I think just x minus 3. Okay, very good. So this means that f prime is equal to 0, that x equals 0, and x equals plus 3. Okay, so let's draw this line here that we had before. Mark 0 and 3. We know that the derivative equals 0 at these locations here, but let's find out what f is doing in between these. Okay, when x is a negative number, then this piece here is negative and this is positive. So we have f prime is negative. The product of these two will be negative. So f is decreasing on this interval. Now what about between 0 and 3? Between 0 and 3, this will still be positive. It's a number that's less than 3 but bigger than 0, so this piece here will be negative. So we'll have a positive times a negative. So f prime is negative, so f is decreasing. So notice here, f is decreasing, and then it has a horizontal tangent here, and then it will be decreasing again. So we're not going to have a local max or a local min here. Now what about after 3? After 3, this value will be positive, and this value will also be positive. So this will have positive first derivative. So f will be increasing. So right away we know where f is increasing, okay, and decreasing. Let's discuss the concavity. So here we set the second derivative equal to 0. Our second derivative was 12x squared minus 24x. This has a common factor of 12x. When we pull that out, we get x minus 2. Okay, so f double prime is 0 at x equals 0 and x equals 2. All right, so now let's draw another number line here. Let's indicate 0, indicate 2. So this is f double prime is 0. F double prime is 0. And let's check the concavity. Okay, when x is less than 0, then this will be negative, and this will be negative. Negative times a negative is a positive, so the second derivative is negative, or I'm sorry, positive. So we get that f is concave up on this interval here. All right, very good. Now, between 0 and 2, this will be positive, and this will be negative, so f double prime will be negative, so f will be concave down in this interval. And then after 2, we'll have positive times a positive, so f double prime will be positive, so f will be concave up. Okay. All right, very good. I'm going to superimpose the graphs or the information that we had about the first derivative as well onto this. So let's just recap. So we had 0. Okay, and then our other critical point, that is where f, the first derivative was equal to 0, was at 3, and then here we had this 2. Okay, so let's divide up all of these intervals here. Okay, and so now let's write down the information we have directly above from here. So from minus infinity to 0, we knew that f was concave up. Okay, from 0 to 2, we know that f is concave down. Okay, and from 2 onwards, we know that f is concave up. So f is concave up here, and f is concave up here. All right, very good. Now I'm going to take this, that's just the concavity information. So now let's just add this information here from our previous page. So we knew that between minus infinity and 0, f was decreasing. Okay. Between 0 and 2, which is up here, that's also between 0 and 3, we had that f is decreasing. And then between 2 and 3, which is also between 0 and 3 here, we have that f is decreasing. Okay. And now after 3, f is increasing here. So we have f is increasing. Okay. So I just used the previous data from the first derivative to plot some of this. Okay, very good. Now, we have a complete description of the information that we have. All right, let's take a look at what each of these looks like. So for f to be decreasing, it's going down, and it has to be concave up. So the graph of f has to look like this. That's decreasing and concave up on this range. Here, we're decreasing and concave down. So the graph has to look like this on this interval. Here, we're decreasing, so this is decreasing, concave up. Here, this is decreasing, concave down. Here, we're decreasing and concave up. So we look like this. And then after 3, we're increasing and concave up. So we look like this. Okay. So this is what the graph will look like on each of these intervals. Okay. So using this information, it's actually quite easy to draw this graph as long as we plot where f passes through these 3 points. Okay, so let's do that. So I'm going to draw one big graph here. And we're going to plot 0, 2, and 3. Now, without doing much math here, our function, remember, was x to the 4th minus 4x cubed. Okay, so when we plug in 0, we get 0, and we know that we have to have a horizontal tangent line right here. Okay. When we plug in 2 to this equation, let's see, I'm cheating a little bit. It should be minus 16. So we get minus 16 somewhere here, and the horizontal tangent line as well. Oh no, I'm sorry. At 2, there is no horizontal tangent line. I lied a little bit there. Okay, but it has to pass through this point. And at 3, there's a horizontal tangent line as well. The graph goes through minus 27. So we have a horizontal tangent line here. Okay. Now let's just take a look at what our graph has to look like. Okay. What our graph has to look like on each of these intervals. Okay. So from minus infinity to 0, the graph must look like that. And then after that, it looks like this. Okay. And then it has to pass through 2. And then eventually, and then continue to look like this till it gets to 3, and then shoot back up again. All right. So if we fill this in here, I'm going to try to do this off camera. We get, so it has to be concave up and decreasing to there. Okay. And then it switches it switches concavity, so it goes to concave down, but still decreasing, and passes through there. At this point right here, it switches concavity, so this is an inflection point right here, as was this one. Switches concavity, and then has to be concave up and decreasing to here. Here it has a horizontal tangent line, and then after that, it is concave up and increasing. So this is what the graph of this function looks like. So this is the sketch. All right. So we learned a first derivative test for maxima and minima. There is a final theorem, which is, it's not the first derivative test, it's called the second derivative test. And this says that, if f double prime, not f double prime, if f prime of c equals 0 and f double prime of c is positive, then f has a local min. Okay, here's the picture of that. So here's the value c. So if f prime of c is 0, so it has a horizontal tangent line, and f is concave up, then this has to be a local min. 2, if f prime of c equals 0 and f double prime of c is negative, then f has a local max at C. Very similar picture. Here's C. So horizontal tangent line at C because f prime is 0, but concave down. Okay, so this is a local max. This is called the second derivative test. So we've learned the first derivative test, the second derivative test, and a couple of elementary techniques for sketching curves of functions. We'll take this to another level in the next section.